You ready? Yeah, we're ready. Yeah? Okay, guys, we're going to start. Hello and welcome to CETI SHAMU's Preliminary Design Review. My name is Severin Polakiewicz, and I am the project manager. I will be discussing the project overview and the baseline design, as well as concluding the slides. Here, Grant Dunbar will be presenting the aircraft design. Brandon Sundow will be discussing the takeoff and landing. Michael Shannon will be discussing the navigation and communications. And Ian Barrett will be discussing the electronics. Please note that we have scope down, so if you see different specifications, that is why. Okay, so SHAMU stands for Search and Help Aquatic Mammals UAS. SHAMU will design an unmanned aerial system to carry a future payload capable of locating sperm whales in the ocean. The unmanned aerial vehicle will be launched and recovered from a research vessel's helipad. Why are we doing this? Sperm whales are a vulnerable species with a sophisticated click pattern. Marine biologists want to deploy listening devices next to located whales. Currently, marine biologists spend weeks with only binoculars searching for spouts over the horizon. An unmanned aerial vehicle system will increase search efficiency, resulting in saved time and cost. Our multi-year user ConOps is the culmination of multiple years of senior design, of which we are the first. Note that the UAV is transported in an SUV truck bed. It is assembled and set up. There is a pre-flight check. It is launched. It enters into the mission. Here it is as a circle, but that just shows the extent of the mission and not necessarily the flight pattern that it will undergo. Once a whale is located, it transmits the GPS location to the research vessel, and it returns to land. Upon landing, there is a turnaround time of 30 minutes to replace the battery and swap the data. This mission can be repeatable until finally it is disassembled. This year, the first 4 steps are the same. After 5, it changes. At 5, we first do a communications range test to 12 kilometers. At 12 kilometers, we test that images are transmitted once per minute. Then it returns and enters into a repeated figure 8 loiter pattern, all within line of sight. It does this until it completes 100 kilometers of its flight mission. Then it lands, we test that we can replace the batteries in 30 minutes, and it goes back up. Note that we are testing in Boulder, Colorado and Pawnee National Grassland, which is where our service ceiling, as you'll see later, comes from. The critical project elements for CETI SHAMU are aerial vehicle design, takeoff and landing, communication with ground station, and flight computer. The functional requirements are as follows. 1, operate in manually piloted mode throughout all phases of flight with autonomous mode capability at cruise altitude. Take off and land from and to a stationary platform obstructed fore and aft. It must be modular with 30 minutes land to launch by replacing the battery and swapping data storage. It must have a 12-kilometer communication range from ground station control. The aircraft cannot exceed 22.7 kilograms takeoff weight. It has a 3-kilometer above mean sea level service ceiling for testing at Boulder, Colorado with consideration for density altitude. The aircraft supports a downward-facing simulated instrument payload that is for the future teams to handle. The aircraft shall be operable in winds up to 10 meters per second to simulate winds on the ocean. And it must have a 100-kilometer ground track range endurance. Our functional block diagram is here. Please note the legend. Anything in amber is designed. Anything in light blue is acquired. Our pilot here controls this controller, which then goes to the radio stack. The radio stack is a part of the ground control station. The ground control station communicates with the radio stack on board the UAV airframe. The radio stack then communicates with the flight computer and autopilot. The autopilot is in charge of the controls and the propulsion and also monitors the sensors as well as onboard sensors. Note that we have included the simulated sensor payload, and these launch and landing systems are included here below as a bungee launch with rails and net landing with sliding posts. Now we move on to baseline design. Note that for baseline design, we have very specific designs, and you'll see how to get to those through the feasibility studies. First, we start with aircraft. We have decided to design and validate an airframe. Here is our current geometry and shape. We have a wingspan of 3 meters and a gross weight of 8.65 kilograms. Performance specifications, 20 meters per second cruise speed and a stall speed of 10 meters per second. Moving on to takeoff, we have selected a bungee launch with rail. Here's a basic diagram showing what we're working with. We have a ramp with 2 rails and a bungee that comes around and stretches. As it stretches, the potential energy of the bungee increases, and this potential energy is then transferred to the UAV as it launches. This bungee is designed to give the UAV a sufficient speed beyond stall for independent lift production. Moving on to landing. We have decided to go with a net with sliding posts. Here's a basic diagram of what that might look like. These dimensions here show that the net will fit on the helipad. These right here are sliding, and they slide up as the UAV lands into the net. What this does is it increases the landing distance, hopefully decreasing the G's experienced by the UAV. A hook will be implemented on the nose of the aircraft to catch the net and to prevent crashing into the ground. For our autopilot and flight computer, we have decided to go with a Pixhawk 2.1 and a Raspberry Pi 3 Model B. Here's a basic functional block diagram showing how these connect together. We have our Pixhawk 2.1, which is our flight computer, our autopilot, and a Raspberry Pi 3 Model B, which is our flight computer. These communicate with each other. We note that there are sensors connected to the Pixhawk, and the Raspberry Pi communicates with the ground station. Our communication system uses an RFD 900 plus data link and an open LRS RC. Here's a functional block diagram of how they are connected. And finally, we move on to electronics. We have selected batteries as our choice. We will design a battery pack connecting batteries and cells and then in parallel to produce the endurance that we need. So we see in our ground station, and our UAV are connected via the RFD 900 data link, and we have an RC link between the open LRS on the ground station and on the UAV.
Moving on to aircraft design feasibility now. We're going to go into a little bit more detail about how we got to where we got and why it's feasible. So first we started with configuration selection of our aircraft. We looked at 4 basic configurations of aircraft: conventional, canard, 3-service, and tailless. Examples of all 4 are shown below there. And as you can see in the simple trait study, we found that tailless or a flying wing aircraft came out on top. This is due to superior airframe weight, durability, and complexity. Though, as you can see, in the future we're going to have to pay a little bit more attention to the stability of the aircraft. Now, looking into the aircraft mass sizing, we started by looking at some historical data of other small unmanned aerial vehicles to see what fraction of the overall aircraft is, for example, the structure, electric motor, etc. So we estimated that the basic structure of our aircraft will be about 35% of the overall aircraft. The electric motor will be about 5% of the overall aircraft. The autopilot, flight computer, RC electronics communication systems will be about 5% of the overall aircraft. And then you can see here is our fixed 2.27 kilogram payload, as well as 2.49 kilograms estimated for batteries. The battery weight was estimated using an iterative process, hence it appears as an absolute mass here. So what we can do with this is we have all these fractions that we know need to go into the structure, electric motor, etc. So what we do is we take the masses that we know and we divide by the remaining percentage of the aircraft takeoff weight. So what we find is dividing the total 4.76 kilograms from the batteries and payload by the 55% of aircraft we have for that, we find that the total aircraft gross weight must be 8.65 kilograms. This is under our 22.7 kilogram maximum takeoff weight given to us by the customer, so this aspect of the project is feasible. Moving on to the fuselage layout, we obviously have to design a fuselage that handles both our pre-specified payload from our top-level requirements, as well as all the electronics, et cetera, that we're going to need for the aircraft. In this case, you can see we also have an aerodynamic forebody and aft body for aerodynamic reasons. And this will also help us be a little bit more flexible with the CG should the aircraft come out to a different center of gravity than we initially designed it to. And so we can see that this particular fuselage will support our payload dimensions as well as all of our electronics, so this aspect of the project is feasible. Now, it'll be approximately right there. All right, moving on to the modular design aspect of the project. Our top level requirement is that it has to disassemble into a box with these dimensions. So we designed the aircraft to break down into the fuselage, which is in those dimensions, 2 half wings, which are each in those dimensions, and 2 winglets, which are in those dimensions. All of these can fit within that box, so this aspect of the project is feasible. This is a very typical breakdown for an RC aircraft or a small UAV of this size. Next, we did some preliminary dynamic stability calculations using these equations of motion. So we're going to start with the longitudinal stability. So obviously at the end of the day, we need an aircraft that is capable of safe controlled flight in both manual and automatic modes. So this is a pretty big aspect of the project. These plots are just from steady level flight. So to do this, we had a combination of Athena Vortex Lattice as well as MATLAB to take a look at our stability. So here's an eigenvalue plot of the longitudinal stability of the aircraft. So we can see that the short period mode is, of course, very stable. But on the other hand, we have actually a slightly unstable phugoid mode. So we're actually going to need to focus a little bit more on this in the future. This is a common problem with high L over D aircraft like the one we're designing. I'm sorry? It was prior in the slides. Yeah. Okay. Now moving into lateral dynamic stability of the aircraft, here are the equations of motion in the lateral modes. Once again, our goals are the same. And so what we find is our roll mode is, of course, stable. The Dutch roll mode is stable, and the spiral mode is actually very close to stable. It's okay for the spiral mode to be unstable. The vast majority of aircraft have an unstable spiral mode. And of course, we can fix all of these instabilities with a control system or even a human pilot.
All right, now moving into the takeoff and landing system. Real quick here, we have a simple free body diagram. Some important things to note are the driving force of this bungee launch system is obviously from the bungee, theta being the launch angle, and this velocity here at the end needs to be about 1.2 times v stall. We said this because we don't want the thing to launch at stall speed, just in case it goes right into the ocean. So there was a question of, can we really use a launching system such as a bungee or a pneumatic catapult here to get this thing to take off and do our mission? And the answer is yes. This pneumatic launcher here, UAV Factory, produces and sells. They have a maximum takeoff speed of 24 meters per second with a maximum air UAV weight of 35 kilograms. So our takeoff system is possible with our weight and minimum takeoff speed. Now, assuming we do go forward with a bungee system, we need to first look into the energy balance of the ramp. So assuming we have a final velocity of 13.3 meters per second, that comes from the 1.2 times v stall, and a mass of 8.62 kilograms, we can use conservation of energy, assuming some friction losses, in order to get a spring constant. Now, this is in this lower blue line here. The K value spring constant is on the y-axis here, and it's a function of the pullback distance. We have a desired value of 3 meters here, and with that, we get a spring constant of 177 0.5 Newton per meter. Now, this K constant is feasible for, like, any spring constant can be feasible. It's just a matter of we need to get a long length. We can get any length we want in order to get any K we want, within reason, of course. Now, one of our derived requirements is the launcher shall launch the aircraft with an acceleration under 7g. That is actually a typo. That should say 8g. We just want to acknowledge that because of the aircraft is going to be experiencing lots of g's during this. The 8g came from our levels of success for the ultimate g-force we want this thing experiencing. So if we look at the red line up here, we also plotted the force for per pullback distance, so force here on the y and pullback on the x. This is our desired value, again, of 3 meters. We get a force to hold that aircraft in the top position of about 530 newtons. Now, that is about 115 pounds. That's a lot. So regardless of what pullback distance or K value we use, we're going to have to implement some type of winching system in order to pull that back and lock it into place before takeoff. Now, if we do a quick G acceleration analysis on it, we get that it is under the 8G requirement, therefore the takeoff is feasible. Just like takeoff, we need to be able to survive the landing and be able to have a quick turnaround time for our aircraft. So assuming that our fuselage has a cross-section area of 0.02 meters squared and we have a 3-meter net height, it'll be pretty easy to get this aircraft into the net. We have a diagram over here to the right, assuming that this is the initial position before the aircraft strikes the net. It has a maximum deflection of 60 degrees there. That gives us a stopping distance of about 1.31 meters. It is an important thing to note that the material that we are going to make the fuselage out of has a compressive strength of 120 kilopascals. Now, taking that 120 kilopascals, we can throw it into the stress equation and find out the number of G's it's going to be experiencing during that time, and we got out about 28.5 G's. That is also corresponds to a minimum stopping distance of about 0.2 meters, and that is much less than the 1.3 meter design we have for the net, so therefore that is feasible as well.
Okay, so that brings us to communication navigation. Okay, so we begin with our communication, our navigation hardware here. We see on the ground station, we have an RFD 900 radio, which will communicate to our onboard components of the flight computer and autopilot. So on the ground control station software that we'll be using, Q Ground Control does not support all of the Mavlink protocols we need. In particular, it does not support image transfer. So we'll be designing a filter to filter out those particular Mavlink messages and handle them separately. Okay, that brings us to the communication radio. We're going to be using the RFD 900 communications, RFD 900 telemetry radio. It is specifically designed for UAV use and is optimized for the Mavlink protocol. We need 22 kilobits for telemetry, and this radio at our 12-kilometer range, we can use its maximum baud rate of 112 kilobits per second, leaving us 90 kilobits extra. So that's feasible. Now on to the autopilot. Beyond control of the UV itself, the autopilot needs to send the proper telemetry to the ground station to provide for a virtual cockpit in Q Ground Control. The autopilot we chose, the Pixhawk 2, with the PX4 Pro, has a triple redundant IMU and a barometer internally, adding a GPS and airspeed sensor gives us all, as well as a compass, adds all of the required data that we need to implement a virtual cockpit on the Q Ground Control, which is handled for us. And on to the flight computer. So the flight computer is the Raspberry Pi Model 3. It's responsible for sending telemetry to the ground station, receiving commands from the ground station, sending them to the autopilot, as well as sending images back to the ground station. So on to the flight computer software. We begin with the communication stack, which consists of the RFD 900 radio, communicates over the Mavlink protocol, and will pack up telemetry at this given rate. Oh, before I get further, Note that blue is existing software, green is new software we must write, and orange is data. So back to this. We'll also have a command handler which will accept commands from the MavLink protocol and pass them along to the various parts of the software via callbacks and broadcast messages. It'll also contain an image packer which will pack the images into 253 byte chunks, the maximum allowed by MavLink, onto the mission manager, which will consist of up to 255 buffers of Mav commands. That's part of the MavLink protocol. It's the mission protocol part, which we will be able to program with these given messages over the radio, MavLink radio. We'll also be able to select which mission to run. This gives us the ability to change mission during flight, such as, oh, we spotted the whales over there, redirect. And now onto the main flight software, which consists of the Pixhawk running PX4 Pro, which we will talk to with Drone Core API. We'll also store the aircraft state, which will log to a file. And we also have the Mav command parser, which is responsible for parsing those MavLink mission commands into C++ objects, handing them off to the flight director, whose responsibility it is to deliver position set points at a rate of at least 4 hertz to the Drone Core API and thus PX4 Pro. This brings us to our faults. We're going to handle 2 faults. One is two main faults. One is bingo battery. We only have enough battery to return and land safely. And also radio failure. In either of these cases, we will return to the last known home location and loiter waiting for operator instruction. And then finally to the imaging system. Imaging system consists of the RPi camera, which we will read images from with RaspiCam, and compress them with libwebp before sending them off to the image packer. We'll also compress them with the standard JPEG format before tagging them with GPS and timestamp data and saving them to the disk, mainly for debugging purposes. As you can see, we've examined all the components needed for the flight control software. Many of them can be filled with existing software and libraries. And then we've also identified parts we need to write ourselves, which is new software. And all of these can be integrated via standard communication and data passing protocols, as well as good old-fashioned function calling. This brings us to image transfer rate. At a required rate of 1 image per minute, this statistical analysis shows that we need a little less than 70 kilobits per second to transfer those images to the ground station using our WebP compression, which is less than the 90 kilobits we had left from our telemetry budget. So we can send these images to the ground station, feasible. This brings us finally to the actual camera module itself and whether we can see these whales on these images. The RPi camera is an 8 megapixel module. We're going to downsample to 2 megapixel before transferring. It has a 62 degree field of view and in our 1 kilometer cruise height that gives us 0.6 meter pixel size, and an average adult sperm whale, as you can see, covers about 92 pixels on the screen. So we can clearly see that it's feasible.
All right, now on to power feasibility. Some important requirements are for our subsystem to be effective. We have to fit in an allotted weight and allotted volume, as well as powering the system, that is the stage, the cruise stage of flight, the climb stage of flight, and all the onboard components. Here we see an equation. This is the mass battery fraction equation, something we derived ourselves. It tells you what percentage of the total weight of the aircraft will be batteries, and it is defined by these parameters right here. This equation only applies to cruise though. Now in order to find the power for cruise, we are going to assume steady flight conditions, i.e. lift is equal to weight and thrust is equal to drag, and we're moving at a constant velocity of 20 meters per second. What do we know? We know our lift over drag, we know our, which is 10, and we know our weight, which is about 25 pounds. And if we use these assumptions and these values, we can find a thrust and then multiply that thrust by the time of flight, which is 1.4 hours, thus giving us an energy requirement. But nothing's perfect, so we add this efficiency factor, giving us 445 watt hours. For climb, we're going to do the same thing. We are deciding to climb at 5 meters per second. We are still moving at 20 meters per second. And with these values, we can find a time of climb
Again, if we use these values to multiply or to find a value for thrust, we can multiply that by the time of climb, add in this efficiency factor, and we get an energy requirement. Here's our power budget. Yep. 3 minutes. Here's our power budget. It has the power requirement, energy requirement, for steady flight, for climb, and as well as all the components that will be on the UAV and the power that is drawn from each one of those components. And if we assume a 10% margin, we will be required to produce 584 watt hours. Now, when we looked at different types of batteries, we were looking at lithium ion. These lithium ion batteries can produce the energy we require, and they are much lighter than NIM batteries. However, the problem with these lithium-ion batteries that produce these pre-made lithium-ion packs that produce this amount of power, they have a low energy density, which is going to cause problems for our UAV. And so if we think about that for a second, the typical design L/D of an aircraft comes out less than the actual, and that's something we can determine via simulation. Now, if that's the case, we can assume, or we will be able to possibly use these low energy density batteries. Now, assuming that we don't have an L/D increase and we are still with 10, we have this battery as an option. And this is just a battery. We'd have to make the pack ourselves. A pack is defined as a group of cells, and a cell is defined as a group of batteries. And for one of these batteries, these are the specifications here. The important specs are that one battery does produce 18 watt hours and they are rechargeable. And if we do some calculations, we can see that 584 watt hours is achievable with 33 batteries. However, 33 batteries does not make a working battery pack. In order for a battery pack to work, we need each cell to have the same amount of batteries, therefore each cell has the same energy capacity. And the nearest number of batteries that gives us that working pack, as well as a desirable voltage and watt hours that fits our requirements, is about 36 batteries, excuse me. And so with 36 batteries, we see these pack configurations here. It is important to note that each pack configuration does in fact produce the same amount of energy. The only important difference is the amount of voltage that each pack does. 33 volts, or we know that voltage, the increase in voltage is more efficient, so we would choose 33.3 volts. However, we don't know if our speed controller can handle that. And from researching other batteries, we know that a standard across LiPo batteries is 22.2 volts. So this would be our pack configuration. That is 6 cells, 6 total cells and 6 batteries per cell. And if we use the specifications from each battery, we can find that we are in fact within our allotted weight, our allotted volume, and we produce enough energy. And as a side feasibility check, we note that each battery must produce less than 1 C draw on average. That is to protect the battery from any harm, as well as allowing the battery to operate in an optimum life cycle. And we did do these calculations. They are in the backup slides. The average draw per battery in this pack configuration is 0.7 C.
Moving on now to the Gantt chart. This is our schedule moving into CDR. First, I'd like you to note that the critical path here is outlined in red. The first thing in our schedule is aircraft performance analysis. This will be a completion of what we already started during our PDR. The integration plans are dependent on the completion of the performance analysis, and they come next. You'll note that they are dependent on this analysis. After that, we have our manufacturing plan and test and safety verification plan, which are all dependent, all of which are dependent on the integration plans. Finally, in the last 3 weeks of November, we will begin our CDR slide compilation. Here's our budget. You'll note that the most expensive component is the airframe with the motor. All of these components summed together add up to about $4,000, which is $1,000 less than the $5,000 that we are budgeted. Now I'd like to thank these people. A special thanks to the PAB, Dr. Coster, James, Dr. G, Dan, Bobby, Tim, Matthew, Cody, and the United States Naval Academy. Thank you for your time. I'd like to open it up to questions.
this on? Okay. So the general impression is you've done a lot of good work. There's a lot of good engineering stuff in here, right? Some good analysis, a lot of detail. So that's really good to see. I think in some cases you were trying to put too much detail in too fast. And in particular in the software section, I couldn't follow anything. You just rapidly listed a bunch of stuff. You weren't really explaining to me how the software basically works. So there's the impression you've thought a lot about what's in there, but you're not conveying any of that insight to me. So think about how much you present and what you dwell on so you can convey something of that understanding, not just list all kinds of stuff. And looking through your presentation here, there must be 30 slides on the software alone. You didn't talk about all those, but still, that's too much to try to get through, right? So be a little more selective. So I had some places where you went through it a little too quickly and I had questions, but even though I interrupted you, I didn't want to do any more than that. A couple things though really confused me. So the battery issue. So the batteries, you mentioned you're using a low energy density battery, and you're also discharging only at 1C, which means you're using a low power density battery. Why in the world wouldn't you use a high energy density battery and a high power density battery?
So what Ian was explaining during the PDR was that the batteries that we showed to you actually have really, really high energy density. The expense of that is really low power density. As the C rating goes up, the weight of the battery goes up. However, we're carrying...
So when he said low energy density, he meant high energy density?
He was talking respective to the batteries that we displayed. So for example, a typical RC battery isn't going to be that energy density. However, if the aircraft were more efficient, we could actually go back to off-the-shelf RC batteries, which do have lower energy density.
Sorry, I'm not following that.
The pre-made battery packs had very low energy densities. So I was trying to convey that if our L over D does in fact increase, we can use those because the power density is a little better.
So you're talking LiPo?
LiPo, yes.
Okay.
And so the point I was trying to get across with this battery is that the energy density is a lot higher, and this will be more feasible with our L over D of 10 if it does not increase.
How much is a lot? You said a lot higher.
Well, with this battery, with making a battery pack with this, we can save 2 pounds off of the total weight.
I don't know how to put that in perspective. So
We can save 10% of the aircraft weight by using these versus traditional off-the-shelf LiPos.
okay, so a lot is 10%
Yes,
here?
of the weight.
Okay. For me, that's not a lot, but maybe for you. Okay. So it would be good if you would compare that with something, right? You said it's a lot more, but if you quantify how much more and tell me what you're comparing it with, then you've got a perspective there, right? I just didn't know what you're comparing it to. What are these anyway? What kind of battery is it?
These are 21700 lithium-ion batteries. They've been recently developed mainly for electric car usage. They're essentially the big brother to the popular 18650 battery, which has been used for years now in to make custom battery packs.
Okay. So these are like a steel case or something?
Yes, they're just
And
larger.
still they have higher energy density than a LiPo?
Yes,
Okay. All right.
about 50% more.
Okay, so that's the kind of thing I wanted to hear, is that comparison number, right? Not just a lot or more or something. Okay, thank you.
Well, thank you. And I echo what the Professor Lawrence said. You had 30 minutes, but you had 91 slides. So some of them you went really fast. And I felt like you did a really good job with earlier, like the aircraft design, all the specifications. Then I started getting a little bit confused later when you talk about especially communication, navigation, the imaging part of it. So a couple of questions specifically. You're going to test it in the Boulder area. So how can you tell if there's a whale there or not?
Clearly we can't detect a whale, we'll be looking for a similar sized object such as a car or
Okay.
anything we can find up in Pawnee.
Just
where we
so
have to
you're
test.
really, I noticed your analysis, you're really emphasizing the dimension, the size of the whale.
Yes.
So, but if you can really detect if it's a whale or not in the ocean, sometimes, the image contrast, that could be very different. So I didn't see that part of analysis. Like, can you really detect that that's a whale there? Or that's just because there's a shadow of some kind of things. So that's one part I was a little bit confused. But the other thing that I was not sure I got it is how do you do the navigation? Is it going to be autopilot, just go to some area, circle around? Is that what you're planning to do? Or is there any kind of interactions or?
Well, that partially feeds into future years. The autopilot itself for this year will mainly be pre-programmed and fly a pre-programmed course, but we need the ability to change direction if a whale was spotted. Also, in particular for future years where there will be an automated whale finding payload on board, we'll need to command the flight computer and autopilot to redirect and follow the pod of whales.
Okay, so that was another part of the things that you're doing this time.
The ability to reprogram in flight and change our flight path
Okay.
and change our waypoints
Okay.
is this semester. But that's in support of future years.
All right. Okay. So the last question is, again, about the image processing. Is that going to be done on board, or is that information going to be relayed back?
This year, we are not doing any image processing. We're just compressing it so we can send it back. In future years, they will be need to do image processing to determine exactly what to send back at a higher resolution than we can currently send back.
Okay. All right. Well, thank you.
Okay, lots of work done, that's obvious. Then considering that you're looking for whales, eventually looking for whales from a boat, I would have welcomed a discussion of the environment that you're going to be operating at. There will be winds, there will be temperature. What is that? What is the temperature? How is the temperature? I guess it's going to be cold or somewhat cold. How is it going to affect your subsystems, including your battery performance? What is the effect of winds on the range that you can cover, things like that?
The customer told us that we will not be operating during winds that exceed 10 meters per second. And most of this whale searching does happen along near the equator. So heat is not going to be a problem for batteries. And
So it's good. I'm glad that you know that, but it's just I'm missing it from your presentation. Yeah. Okay. Cost. If I look at the very few pictures of your launch and capture mechanisms, my guesstimate is that those are severely under. Those numbers are severely too low. What it really is going to cost to build a launch system that will give you the right amount of G. Do you have any base on how you estimated those values?
most of these are estimations like the airframe, some like the Raspberry Pi, these in-depth components come from
I'm sorry, launch system and the land
a
system
launch system.
in particular.
The launching system is a bungee system. We got those numbers. So when I was doing my research for different launching systems, we found multiple variations. So there was as small as little hobby planes. They could build those out of PVC pipe for like $10 almost. And then there was obviously stuff on the full scale that was like just launching actual high-end military drones. There was no good definite middle ground. So this is just what we assumed with just getting raw materials from the market.
Okay. Should I move on, or do I have time for more questions?
You said rails, but the launch system is more than rails.
Right. Exactly.
The release mechanism, yes, it's going to be a lot of things in there. Yeah.
Is that in there?
We were considering using a manual winch to save cost. So not electric winch, but a manual.
Two more quick questions then. Are you designing for water recovery in case of malfunction?
No.
So you're willing to lose the aircraft? Okay. And You mentioned something about bingo battery, which is your aircraft is going to calculate what is when it needs to turn around and reach the boat, right? Is that correct? Did I understand it correctly? How is this possible without knowing what are the wind conditions? And how is this, is it going to be measured eventually on your system?
Yeah, so knowing how much battery draw knowing how much battery capacity we have, we'll be able to monitor battery draw during flight, so we'll know when we reach a certain level. This all depends on us knowing the winds. Naturally, any wind estimate from the UAV itself is going to be a rough estimate, and so we'll need to add safety factors in there to account for that. In the worst case scenario of our maximum winds, it may be necessary for a pilot to bring it back early.
Right, so it depends on whether you're upwind or downwind from the boat.
Yes.
Okay.
In a worst case scenario.
When you talk about landing, you say that your landing distance is 1.3 meters. Where does that come from?
Our landing distance comes from a preliminary estimate of the size of the net being 3 meters high and a 60-degree deflection distance with the sliding posts. We didn't have any real-world examples, so I chose some realistic seeming numbers based on videos of similar landing systems.
Okay, and when you look at if the structure is supposed to fail during landing, you look at compressive forces. But what about possible bending or torsion of the wing? Or, I don't expect it to fail in pure compression, but other things happen during landing.
Yes, we do have concerns with bending moment of the wing. Those calculations were also done. I believe they might be in the backup slides.
I think you have some for flying, but not for landing, from what I've seen. I don't know if...
Yeah, so we didn't do any torsional estimates because we don't know the full dimensions of the aircraft yet. I did make an assumption that the longitudinal forces on the fuselage would be the biggest driving force during the landing, just because we do have a tailless configuration with a highly swept wing. So ideally, the fuselage will be impacting the net first and will take most of the force.
I'd like to see some numbers on that down the line. And then you say you have a hook to connect to the net?
Yes.
And if the hook fails, just bounce back, or do you have an idea of how elastic or inelastic that collision will be?
We do not know how elastic or inelastic the collision will be. I assume the force of the initial stopping distance would be more than any of the subsequent forces from bouncing around. So I didn't calculate any specific elastic numbers.
Okay. And for the takeoff, you mentioned some numbers for the bungee that you need to have. Do they sell those? Can you get those numbers for a reasonable material at a reasonable cost?
Are you talking about the spring constant?
Sure, yeah.
Yeah, so basically, if we know the force that we want to hold it back and we have the distance we want to pull it back, we can manipulate any K by just having just a longer rope per se. We can get any K value we want, but within reason.
But are those, with a distance that is reasonable, do you get numbers that you can buy? Or do you need
so
25 meters of distance to get those numbers?
Repeat that last line?
Or would you need 25 meters of distance to get those numbers?
We have yet to figure that out, but we are assuming that we will be able to get any K value we want.
Just to add on to that, if you find a bungee, we assume that we could find a bungee within reason of that, so we still have to look into those materials going into the CDR, but we assume that if we put them in parallel, we can get up to that number if the bungees aren't strong enough.
Right. And I think that's besides things that have been asked already.
Sure. Are you done? Sure.
Yeah, yeah, there was a lot of good stuff in here. The biggest thing I'm concerned about is it seems like the major portion of this project is designing an aircraft, and there's really not much as far as the aircraft is concerned. There's some really high-level feasibility stuff on the aircraft, but not much on the aircraft itself. And that concerns me a little bit because this is fairly large for the type of aircraft that student projects have built in the past. So you've got this 3-meter wingspan, and so there's, like I was telling one of the other groups, there's a lot of devils in the details here. There's structure in this aircraft, there's materials in this aircraft. So have you looked at, when you get these, for example, these mass budgets, I mean, have you kind of thrown this aircraft design together? Do you have a skeleton? Do you have the skins? Do you have the materials picked out? How do you know that mass is actually correct without knowing any of the internals of this aircraft?
So that's based on historical data. So the way aircraft design is taught at CU is you start with these initial estimates when you're doing your conceptual and preliminary design using historical data, and it will be up to you later in the detailed design to actually engineer a structure that'll do that. The 35% was actually a fairly high value for structure. Yeah.
Okay, so basically you're doing it on comparison.
Effectively, yes.
Okay. I guess I would ask that you also give some comparison as to whether this group can do that. So do you have experience building aircraft this size?
I do, in fact.
Okay. And you're just one person? Does anybody else?
I believe we have several other people in the group who've built RC aircraft before.
All right. I mean, I'd like to see something related to feasibility related to this, because it's harder than you think to get these things built and flying. So it has been done, but there's not much information here. There's 2 slides on the design of the aircraft itself.
Yeah,
and it seems to be most of the project other than the software.
We actually do have some additional slides in the backup slides, including a preliminary structural analysis.
Okay. I may steal something from Bobby here, but you did all this analysis on the batteries here, and it seems that your motor and your flight controller and all these other components require probably different voltages and currents, and I didn't see anything about circuitry to regulate those supplies or anything like that. So it seems missing.
Well, commonly in RC aircraft, in literally every RC aircraft any of us have ever seen, all the systems are run off of 5 volts. I know for a fact that's true of the RC systems we're going to select, including the flight computer and autopilot. Now, the motor, it's going to be a brushless motor, so it's a 3-phase AC that is handled by a commercial off-the-shelf speed controller.
Yeah, no, okay, I get the components, but you have to put them together. So do you just solder a wire onto the battery pack and then hook it up to the flight controller and it all works?
That's not too far from the truth, yeah.
Well, sorry, I find that hard to believe. Okay. And then I guess last thing, maybe you guys can teach me how RC motors work, but you have this 1100 watt motor. You know, what prop are you going to pick for this thing, and what kind of efficiencies do you have, and what kind of currents is it going to draw, and how does that, over time, how does that bounce up against your power budget? I didn't see the connection there.
Yeah, that's an analysis that we're going to perform going into this next phase of the design process going into CDR.
I'm just curious how you pick an 1100 watt motor.
Yeah, that was based on the power requirements of the aircraft. So that's derived from specifically the L over D of the aircraft. So you have like a power required equation. And then now that's going to give you your required power for various phases of flight, such as cruise, climb, etc.
So does this thing just run it like quarter or half throttle at different parts of the flight, or?
Yeah, exactly.
It does?
Yeah.
Okay.
Yeah, it's totally throttleable.
All right. Well, okay. Does the flight controller just magically does all that?
Yep.
Okay.
I don't need that. And it comes from our climb power derivation. So using all these, I'm not going to walk you through it, but using this process, we assume we get, with the 0.7 efficiency, we get a total climbing power required of 1100 watts. So
Okay, so that's where the motor comes from. All right, and then you factor that into the overall power in the time of the climb analysis. Okay, All right.
I just need to interrupt real quick. So Tim and I actually have to head to class soon. So who has not signed the attendance sheet?
Yeah, Savant.
So I know you guys are still in the selection phase for a lot of this, but in terms of the base materials for the aircraft, I didn't hear what you said you're using for it, but what baseline material are you going to use, and have you looked into how it interacts with highly corrosive environments like flying over an ocean?
We're still working on our materials selection. Right now our baseline materials are going to be expanded polypropylene foam. We're experimenting with different coverings for that in our mathematical models. We have not done an analysis for corrosive environments yet. Rashab.
I might have missed this, but I saw that your net diameter and your wingspan are about the same, right? How does that sort of like navigate into the net? Is that manual or is that automatic?
The net that we illustrated was just for illustration. The actual width will be much larger, and this year our base level of success will be a manual flight into the net.
Okay. Also, real quick, Rashab, the net right there is 6 meters wide and the wingspan is 3 meters, so it's already double. Yeah, thanks.
Yes.
So the frequency at which you're taking pictures, how is that determined?
That was pretty much given by our customer. So that's just a requirement from them. We are missing pictures. The key to that is, as again, future years, we'll need to develop the actual whale sensing payload, which will determine only and find only images that are likely to contain a whale and send only those back instead of all of them.
Okay, we'll wrap it up there. So you're still waiting on sign-ups?
Can I ask a question? Can I ask a question? What's the first thing to get dropped when you fall behind schedule? Because you have a lot of different things that you are doing. Can you at least talk about your priority scale?
Okay, I mean this jokingly, but the VTOL system.
Well, you dropped that. What's
Yeah,
next?
we already dropped it.
I still feel like you have a lot of stuff. So don't answer that. Let's play a different game. Can you all raise your hands when I throw up a subsystem? Because I want to know who's going to be working on these different things. So the custom battery pack, 2 people. The software, 2.5 people. Not to say you're a half person, but you're fluctuating. The airframe, a lot of people, good. Redoing the airframe after you crash it.